Okay, so we obviously in that very last example saw one rational root and two irrationals. Now we're going to see how complex roots come up. So a polynomial of degree 5, whose coefficients are real number, has the zeros 1, 5i, and 1 plus I. Find the remaining two zeros. Okay, so I don't think I mentioned this yesterday. I know I mentioned, obviously, and I just mentioned again, that irrational roots come in pairs of 2. But not just 2 anything. They come in pairs of 2 conjugates. Like positive root 5 that we just saw and negative root 5, those are conjugates. 0 plus root 5, 0 minus root 5. So you should remember this from last year, that imaginary roots also come in pairs of 2 conjugates. That's really the only fact you have to know to be able to answer number 1. Because they're giving us 1, and that's a rational root. They're giving us 5i. So that imaginary root has to come with a conjugate. So if 5i is a root, what's the other root? What's the conjugate of 5i? Technically that's 0 plus 5i, so the conjugate would be 0 minus 5i, right? Which would just be negative 5i. So there's a pair of imaginaries. And then 1 plus I is an imaginary root, and the conjugate of that is what, Ryan?
1 minus I.
Good. So we've just found the 2 remaining. It was a degree of 5, so we have 5 total. The 3 that they gave us and the 2 that we had to fill in the blank on. Okay? And then we need to write the equation of polynomials as well. You did this last year. Find a polynomial of degree 4 whose coefficients are real numbers that has the zeros 1, 1, and negative 4 plus I. So the polynomial function that you just have to know to work with, if you had me last year, this was on a flashcard. X minus your root, X minus your next root, so I'll do root sub 1, root sub 2, dot, 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 depending on how many roots you have. And so if you have a 0 at 1, then your root is 1, so the factor would be x minus 1. Does that make sense? And then you have another root at 1, which this could have been written as you have a double root at 1, which means you just have to do this twice. And then you have a 0 at negative 4 plus I, and where else? If imaginary roots come in, right, if they come in conjugates, negative 4 minus I. So this is a little tricky because when we do this for, let's start with the negative 4 plus I, when you do x minus that root is a binomial. So when you subtract a binomial, you have to make sure you keep it in parentheses initially. I'm going to make that set of parentheses bigger. And you have to actually distribute that negative sign, which is going to change that into x plus 4 minus I. And then the last root, x minus, and again another binomial root, negative 4 minus I. And you have to distribute that. That'll become x plus 4 plus I. So this is a function, this particular problem doesn't give us any additional information to figure out the value of A. A lot of times they'll give you a point that the graph has to go through, so you'd plug that in for X and Y and calculate A. This just says any polynomial. So A can really be any number you want, but it does say polynomial. So you have to multiply all of this out, which sometimes you'll have to multiply everything out if it says polynomial, sometimes you don't. But no matter what, if there are imaginaries, you definitely have to multiply that out no matter what. Now there's two ways to do this. You can treat this section as a trinomial times a trinomial and distribute your x to the 3 terms, then distribute your 4 to the 3 terms, then distribute your negative I to the 3 terms. That's long though. Or you can choose to see these as conjugates. You have x plus 4 minus I and x plus 4 plus I. That's just going to save you time because your outer and your inner are going to cancel, right? When you multiply conjugates. Does everyone see that? Yeah.
So the thing that makes imaginary root conjugates is like the sign that's in between the I and the number rather than the x. 'Cause like,
well, initially it was x minus the imaginary.
right. I just mean like, you know how this is the same sign?
Yeah.
So the only sign matters in terms of conjugates.
Not really. Like, I'm going to make up a totally different example. I could do x minus 4 plus I and x plus 4 plus I. And those are conjugates. Do you see that? It's almost like you're doing, you need to do a mental grouping to kind of call this like binomial minus I, binomial plus I, versus here it's x minus binomial, x plus binomial. These are conjugates too. Why would I, should I rewrite that? What I just erased? Were you talking?
Do you ever add the root, or is it always x minus the root?
It's always x minus the root, but if the root's a negative number, it'll turn into plus. Like x minus negative 5 would turn into x plus 5. Do you follow that? So we're just going to multiply all this out. If you don't want to use the conjugates part that I'm talking about here, you get the conjugate just on a binomial, correct?
Yes.
So that's really all that's most important. I only use the conjugate way of multiplying trinomial times trinomial here because to me it makes it easier. If it makes it harder for you, then you can go through and distribute your x to all 3 terms, distribute your 4 to all 3 terms, and it'll be the same thing at the end.
I think I got it.
Okay, so I'm going to treat this, think of it as binomial minus I and binomial plus I. So that's where I'm kind of visualizing the conjugate. So if I multiply x plus 4 times x plus 4, binomial times binomial, I'll get x squared plus 8x plus 16. Then my binomial times the outer and my inner times the binomial I can totally forget about. Because with conjugates, those will cancel. That's why I like doing it this way. And then negative I times positive I is negative I squared. And negative I squared is the same thing as what? Minus negative 1, which would be plus 1, right? So this whole thing becomes x squared plus 8x plus 17. And then we have x minus 1 squared and y equals. Again here, I'm just going to assume a is 1. Now, technically it says polynomial. So, and this was the same in Algebra 2, you just have to go through the annoying step of actually squaring that out, which will be x squared minus 2x plus 1. And this is just a lot of complex Algebra 1, really, just distributing. So I made that a polynomial, and then last step would be doing the trinomial times the trinomial, which I'm going to skip just for the sake of making this go faster. But what I do, and I'm going to type that version of it into my calculator just to show you. What it looks like and where this whole A concept is going to come in. So don't worry about multiplying that out right now. I'm starting with negative 10 to 10. I don't know if it's going to be big enough. It's not big enough. Maybe it is. I'm going to go to negative 20 to 20. Oops, I don't want to do that. Okay, so I had to go from negative 100 to 100 to see this portion, because prior to this, I was going negative 10 to 10, but I was only looking up to like here. Do you see that? So I was not seeing any of this. But now that we see this whole picture, going back to your four roots, first of all, it's a fourth degree polynomial, so can we see the even behavior, the fact that it has the same end behavior? Starts towards positive infinity, ends towards positive infinity. And then you can see your double root, the bounce, at 1, so that accounts for that. The imaginary roots present themselves as a fluctuation someplace else on the graph, but not enough to hit the x-axis to make a real root. Does that make sense? So here's our double root, and then this little squiggle section over here that doesn't create another real root, but that's where your imaginary roots are kind of showing up. Does that make sense? Okay. Now, I plugged this into my calculator with an a value technically of 1. If I change that and put an a value of 2, how do you think that would change the look of the graph? Any guesses? A multiplier of 2 out in front is a vertical stretch, right? If I have an f of x and I compare it to 2 times f of x, when you put a 2 out in front, it's going to stretch it vertically by a factor of 2 from the x-axis. So it does get stretched taller and skinnier, right? The roots aren't going to change. That double root still was there, because if you were on the x-axis and you're doubling from the x-axis, if you were already on it, you're still going to be on it. So it's stretched vertically, so our roots are the same, but it got pulled up. So what we will eventually get to is they won't just say any polynomial where a could be anything. They'll actually give us that it has to go through 17, a y-intercept of 17, in which case that would be the bottom version. Or they'll say it has to have a y-intercept of 34, and then you'll know the point 0, 34, and you'll plug it in, and you would find that the a is 2. You guys did this last year, where you had to find the appropriate a value. Here, with the way it's worded, it says find a polynomial, which means any polynomial. A can be anything, as opposed to finding the polynomial as if there's only one of them. Any questions on that? Okay. On the next one, find an equation of least degree with rational real coefficients whose roots are I root 2. So if I root 2 is a root, what else is? Negative I root 2. And 5. 5 is a rational root, so we don't have to worry about a conjugate with that one. So our factors are x minus 5, x minus I root 2, and Sarah, this is where your double negative is going to come up, because it's x minus the negative I root 2, which will turn it into x plus the I root 2. And again, there's no information about a. There's no additional point that this has to go through. So we'll just assume a can be anything. We'll treat it like 1. And then you can leave things in factor form like we did up there. Sometimes this one doesn't say a polynomial. It just says any old equation. So I don't have to multiply everything out, but I always have to multiply out imaginaries. You can't leave imaginaries, hence the reason it says real coefficients. I can't have that imaginary coefficient. So I'm at least going to multiply out this portion x times x is x squared. Those are conjugates, right? X minus I root 2, x plus I root 2. So my outer and inner I can skip. And then what is negative I root 2 times positive I root 2? Well, don't try to do too much in your head. Initially, what is negative I root 2 times positive I root 2? A negative times a positive is a negative. I times I is I squared. Root 2 times root 2 is 2. But I squared is negative 1, right? So this is what you were trying to do all in your head. Negative 1 times 2 is going to be positive 1 times 2. So that's just going to turn into x squared plus 2. This one doesn't say polynomial form, so that's definitely my that I'm not going to do any more work than I have to. I would leave that as my final answer. Whereas the previous one, the only reason I didn't go further was because I was being lazy. And Allie looked burnt out.
I don't like this.
You don't? Do you remember it from last year?
Yeah.
It
just takes a while.
It does, yeah. It's really only annoying when they make you do it in the polynomial form. It's not that bad other than that, I don't think. But that is definitely just obnoxious. Okay. So here is finally where they're going to tell us about our roots, but they're also going to give us a point that it has to go through. So A is definitely going to matter here. How far we vertically stretch or compress this has to be in such a way that we catch the point 3, negative 150. So your format that you just have to memorize and use is y equals A, and then we need it's a 4th degree, so we need our 4 factors. Mike, give me one of them. I need a factor. Good. JR, give me another one. Good. Alyssa, give me another one. And Laura, give me the last one. Right. So Alyssa really gave me the root of negative I as her factor, x plus I. Good? Now, you can now plug in the 3 and then the negative 150. I usually don't do that yet. I always try to get rid of the i's right away so I'm done with them completely. So I would multiply that out first. I get x squared, my minus ix and my plus ix cancel. And I get minus I squared, which is what? The same as minus negative 1, which would turn into plus 1. So if you can do that piece all at once, I would never have tried to do that up above where there was a negative sign and an I squared and root 2's happening. That was too much, so I took that one a little bit slower. But positive I times negative I squared, and knowing that that's plus 1 is reasonable. So now from here is where we will use our point. We have to hit 3, negative 150. So our x coordinate is 3. Our y coordinate is negative 150, so we plug those in. And that's going to be 5 times 1 times 10, which is 50, right? 50a. So if I'm solving for a, I'm just going to divide both sides by 50. And a is negative 3. So we pretty much had the entire function written here, with the exception of we didn't yet know what a was. So now we're going to just plug in your a value of negative 3. And I'm going to call it a day out of laziness on this problem. because it does technically say polynomial. So we would have to multiply that all out, which I don't think you need to be instructed on. I hope. I don't know, do you? Do you want to see that? No. Of course not. And the last one. Why don't you do this one on your own, and then we will reconvene. Bless you. Are you stuck, Allie, or are you done? Oh, good.
Pick three numbers between 1 and 15.
Three numbers. 3, 8, 15.
Allie barrier is in that bunch. 3, 8, and 13. Before I start, does anybody have any questions? What? No, those aren't the numbers you're doing. Those are the people's whose papers I was going to use to show. Sorry. Okay. I have 3 papers. One of these people thinks that A is 1. The other one thinks that A is 2. And the other one thinks that A is 8. So we clearly have a problem.
Let's vote.
We don't need to vote. We need to review. So let's start with this one. This person had a root at -3, so they made x plus 3. They had a root at I, so they did x minus I, and because of the conjugate, they did x plus I. Then they multiplied those out.
Yeah,
Yeah.
they just didn't, 8 divided by 8 is 1, yeah.
Oh, I hate when that happens. So that should have been a 1. That should have been a 1. You're telling me this is all good.
That's some good stuff.
That's some good stuff right there. So it shouldn't be, oh, first of all, they also didn't distribute their 8 right anyway. It would have been 8x plus 24. But it's 1x plus 3. And then they needed to multiply that out. We like that one? Good. So, oh, this is you?
Yeah, it's an adding error. I didn't do 1 plus 1, and then I did 1 plus
Here.
1 at the bottom.
Right. So you did the conjugates right, you multiplied them right, you changed it to x squared plus 1 right, but when you plugged in 1, 8, 1 plus 1 should have been 2, and that'll fix your problem. Can you hand that back to him? And so then we really like this person's?
Sure.
Well, they got the A of 1, so I'm assuming. Except for they just hadn't yet written it as a polynomial. So x cubed plus x plus 3x squared plus 3. And then your polynomial has to be in the right order. So 3x squared and x have to switch spots based on the order I did it in. Good. Whose was this one? And so this was Mike's. So actually it was better. It looked nerve-wracking when I saw 3 different A values. Okay, you're only doing the odds. The one thing that really didn't come up, and I want to talk about it first, is on this first example. Your degree is 3, so you have a 0 at 4, right? So what's the factor? X minus 4. You have a 0 at 2 plus root 3. So when you do x minus that root, because it's a binomial, it has to be 2 plus root 3 in parentheses, and you have to distribute that, yes? And also, if 2 plus root 3 is a root, what else is a root? 2 minus root 3, because irrational roots come in pairs of conjugates. We saw a lot of imaginary root conjugates in the notes. We talked about this, but this is the first that you're actually seeing the need to do a conjugate 2 minus root 3. So again, with this one, you'd have to do x minus 2 minus root 3. Just like imaginaries, the first thing I would do is distribute my negative 2, or my negative in both of these cases. And then, just like imaginaries, I don't like dealing with imaginaries. I also don't like dealing with radicals. So the first thing I would do right from the get-go is clean that up. Just like you do with the imaginaries. Okay? Just to get rid of them. Because, again, your coefficients have to be real and rational.
It's good.
What did I do to deserve this?
I'm gonna file a complaint.